Welcome to this next module of the NPTEL online certification course for CMOS digital VLSI design, and we start the second part of the inverter. In the first part we have seen the static characteristics of an inverter, how do you draw a voltage transfer characteristics which is VTC, and then how do you extract the switching threshold and the noise margins from the VTC. We have also understood that if these noise margins are available to you, on which parameters these noise margins and switching thresholds are dependent. What we will be looking in this section on this slide or this module are the following. We will be looking at the concept of propagation delay, right. We will be looking at inverter capacitances. The main reason, the motivation for this lecture is that at the end of the day, when you are actually having a large chip, right, and you have primary input and primary output available to you, then you should know how much amount of delay is there between primary input and primary output across the critical path, so that I could extract the total frequency or the maximum frequency of operation of the chip. And therefore, estimation of propagation delay in a chip is an important fact. For that we require to have a knowledge of capacitances and resistances, and therefore this is dedicated, or this module is dedicated to find out the basic inverter capacitances, on which factors do they depend. We also look into the optimal value of the NMOS to PMOS ratio, means we have just now studied, if you remember correctly, just few in the previous lecture, that you require that the aspect ratios of PMOS should be about 2 to 3 times larger as compared to that of the NMOSs, in order to have a symmetric VTC or the voltage transfer characteristics with Vm approximately equals to VDD by 2, which is a natural coincidence or a very ideal value. But in many of the cases I do not want a symmetric VTC to appear. I want that it should be shifted either to a high towards more towards VDD or less towards VDD. So, I can make it VDD by 4, or I can make it 2 by 3 VDD and so on and so forth. So, then at that stage what should be my optimal ratio size of NMOS to PMOS, that we are looking at this point. Then as I discussed to you in the last part of the previous lecture, that I generally have an inverter chain developed, or I have a cascaded inverter chain which will take care of its activity as a buffer, right. So, we need to know the sizing of this buffer chain, for this buffer chain, right, such that I get the minimum delay. So, minimum delay conditions have to be found out. So, what we will be trying to do here is we will try to size the each inverter aspect ratio of each inverter pair such that I get a minimum delay between input and output. We will look into the various understanding of power dissipation, very important idea. We will look at leakage currents and static. So, there are 3 parts of dynamic, we have got 3 parts of power dissipation. One is dynamic, one is static, another is basically a leakage, one is short circuit, another is leakage. So, we will take all the 3 individually, power dissipation, and we will be studying how does power dissipation works. So, the first 4 points which you see here are primarily to do with finding out the value of C, and this is primarily to find the value of power which you get, right. And then we end our discussion with EDP and PDP, which is energy delay product and power delay product, right. Let me come to you the basic fundamental principles of propagation delay. You must have understood how do you define propagation delay is that suppose I have an input transition taking place here, I have an input transition taking place here from 0 to 1, and the output is going from say 1 to 0, right. Now, obviously if you see, this is actually shifted in this direction because of the delay. So, we defined like this as the difference between 50% of input rise. So, this is the point where you have 50% of input rise to 50% of output fall. This is 50% of output fall, right, and this 50% of input is this difference. If you look very closely, this difference which you see is referred to as my propagation delay, 50% propagation delay, right. So, I will have something like this difference is my TP propagation delay. Propagation delay from what to what? From high to low, because your output was going from high to low, right. So, this is defined as propagation delay. In this case TP, 50% of the input rise to 50% of input fall is defined as my propagation delay. Now, since it is 50%, so I can safely assume in voltage domain, so it was 0, this is VDD, right. So, I can safely assume that this point is effectively VDD by 2, right. So, if this is VDD, this is 0, so it is VDD by 2. So, I just need to find out at what point does VDD by 2 happen for input, at what point does VDD by 2 happen in the output, find the difference in time domain, and that will give me the propagation delay. So, if you look here, I get TP, this is the formula which we use. So, remember it is V by I is equals to R, very straightforward. So, I get V by ID sat into 1 plus lambda V, this is primarily because of CLM, and we vary from VDD by 2 to VDD, because that is the transition we are doing. So, from input 50% to output VDD we are trying to find out, and R equivalent will be given by this formula. Actually, please note there is a mistake here, a lambda will be inserted before VDD. As you can see, therefore, higher the value of lambda which you see, smaller will be your R equivalent. Higher the value of lambda implies that your CLM will have such a profile, right. So, rather than ideal value of lambda equals to 0, if lambda is very high, what happens is that it is almost like this slope, which primarily means that if this is VDS versus IDS, then here even if you change VDS by large amount, your ID is not changing. So, del VDS del IDS is approximately is approximately infinity. So, which means that is current source, but as you make it more and more slopey, right, your resistance starts to fall down, and this is exactly what is happening. So, as you make your lambda higher and higher, 1 minus that goes on decreasing, and as a result R equivalent goes on decreasing, which means that the resistance offered by the device is actually reducing. As you can see here, this is the charging flow. So, I have got VDD charges through R equivalent P, switch model charges C load, and your NMOS was switched off. In the second half cycle, when NMOS is switched on, it becomes R equivalent. This was switched on, switched off, and this capacitance was discharging its current through to the ground. With this knowledge, we therefore conclude that for this case, therefore, so I got this as my this thing. So, I defined TPHL. TPHL is defined as the propagation delay for the output to go from high to low, right. So, please understand TPHL is basically the propagation delay for the output voltage to go from high to low, right. So, from generally we refer to this as high to low means 10 to 90%, you can also be doing it. This is approximately equals to 0.69 ln of R equivalent to CL. We got it from the first derivation of the first differential equation of RC coupled circuits. Similarly, TPLH, which is, so this is basically TP output is going from low to high. So, this is low to high, and this is TPHL, high to low. So, you see, so TPHL high to low will have R equivalent N, whereas TPLH, which is this one, will have R equivalent P as the value here. In both the cases, CL is the same. We define the overall propagation delay as the average of the high to low and low to high, and this comes out to be R equivalent P plus R equivalent N divided by 2 into 0.79 into CL, where CL is the load capacitance. We come to therefore, so we therefore in the previous slide, we have if you know the value of R equivalent N and R equivalent P, you can calculate the total resistance or the average resistance seen by the device to the current flow. We are just now therefore trying to find out how will your CL change, or what are the factors which influence the CL value. The next slide will make it clear. If you look here, I have one inverter here, I have another inverter here. So, one inverter is driving another inverter here. So, there are two inverters driving each other, that is what you see in front of you. And as you can see here, that this, as we discussed in our previous understanding, CDB2 is basically drain to bulk of the second transistor for M2, drain to bulk, right. So, this is drain to bulk, this is drain to bulk, I am sorry, I will just make it clear to you. This is drain to bulk is this one, right, appears here, drain to bulk of 1 is appearing here, right. We have gate to drain, or gate to drain is basically gate to drain, this one. We also have the wiring capacitance CW coming here, and please understand this is the gate capacitance for 4 and gate capacitance for 3. This is the what does it tell me? This is basically gate to source. So, CGS, so you can as well write out CGS4 and this to be a CGS3, gate to source, right, very important. And as I discussed with you, it consists of C ox and C depletion when we were discussing earlier stage, but primarily C oxide is there available to you, and we have to be very careful about its wiring. So, as you can see, this is gate drain diffusion. We have a diffusion capacitances here. CW is the wiring capacitances, primarily the capacitances by virtue of the wire available to you, and CG3 and CG4 are nothing but the gate capacitance of fan out. So, this is the fan out here, fan out is 1 here, and therefore it is basically 2 devices M4 and M3 whose input capacitance is a CG. So, if you look very carefully, the output capacitance of the first inverter also consists of the input capacitance of the second inverter. So, if this is the first inverter and the second inverter, the output capacitance of so if this is the first inverter and this is the second inverter, then the output capacitance of the first inverter, which is CL here, will consist of the output capacitance of the first inverter and the input capacitance of the second inverter, right. So, these will be in parallel and they will be added up and you will get a CL value here, fine. So, I think I have made it clear that what is the composition of these values of inverters. Now, what is the gate to drain? Gate to drain, please see in the previous slide, gate to drain is this one, this is gate to drain. So, I have gate to drain, you have got gate to drain here. So, if you have gate to drain, you will see that M1 and M2, the 2 transistors NMOS and PMOS will be either in saturation or in cutoff. So, under this condition only there will be CGD1, right. So, there will be CGD1 only in this condition and there will be no other condition available to you, as we discussed in our previous discussions, that the gate to drain capacitance is CGD1, right. So, if you look at CGD1 here, I will explain to you what I am trying to say. CGD1 is gate to drain of 1. So, this is drain, gate to drain of 1, right. This will appear when M1 and M2 are either in saturation or cutoff, because if they are in cutoff there will be no channel formed there and there will be therefore directly gate to drain will come into picture, and in saturation obviously you will have gate to drain available to you. Now, let us see what happens in a general design issue. So, the design issue is, let us suppose like this, that I have got maybe a NMOS here, right, NMOS here, right, and let us suppose I have a CGD1 and I have give V in here and I have V out coming out here, right. So, what I do, let me say I give delta V change here, this is CGD1, delta V change here, then I will get a delta V down here. So, if because there is a phase difference between gate and drain, so if delta V increases there is a delta V drop here available to you because of this phase change. Now, what I do is this means that if you remember Q equals to CV, or in other words, if you want to find out the capacitance, C is equals to Q by V, which means that if you change on the input side by delta V, you get a change delta V. So, what is the net change? Net change is delta V minus of minus delta V, which is 2 times delta V, which therefore C equals to Q by 2 times delta V, right. If you take this side, on this side I get Q equals to therefore Q by delta V is equal to twice of C, which means that looking from the output side, the capacitance which was CGD1 here will now become under this condition will now become what is known as, you will get 2 CGD1. This is what you will get, this V out here. This is known as a Miller capacitance. So, how do you define a Miller capacitance? Miller capacitance I will again explain to you, because this is quite critical, that as you increase the value of delta V here, right, your delta V there will be decrease in the output side because of the phase change, which primarily means that for every, so therefore the change will be delta V minus of minus delta V, which is plus 2 delta V, C is equal to Q by V. Now, if your V changes by twice delta V, so Q by 2 delta V, take 2 on this side, I get Q by delta V equals to twice C, which means that this for the same change in the output side by delta V is equivalent to saying I have got a capacitance 2C in the output side, right, 2 CGD1, which means that input capacitance looking at CGD1 will appear to an output side as 2 CGD1 under such a criteria, right. So, you if you do not consider this, we will be underestimating the overall process parameter, and that is the reason you see here that CGD is equal to 2 CGD0 into W, right. Why? Because we have to multiply with W, because this is per unit width, and therefore if you multiply with W I get the total CGD, and we multiply by 2 for the reasons we just now developed, where CGD0 is the overlap capacitance per unit width, right, which we discussed in our previous discussion. There will be also, remember, drain to bulk, because if you remember in our previous discussion, this is bulk, which is P type, and this is N plus type, this is P type. There will be always a diffusion layer here, or there will be always a depletion layer here and here. So, there will be always a reversed bias PN junction between the drain and the bulk and source and the bulk, right. As a result, there will be always a reverse bias PN junction. This will result in a diffusion capacitance given by this quantity, which is equals to K equivalent multiplied by Cj0, where Cj0 is the junction capacitance at 0 bias. So, 0 bias means when you did not apply any bias, just because of the doping concentration differences, there will be a depletion region and a capacitance will be formed. As you make the reverse bias more and more, you end up having the depletion thickness larger and larger. So, as a result, Tox or the thickness becomes larger, capacitance starts to fall down, or capacitance starts to decrease at a higher negative gate voltage. Now, K equivalent is just a multiplication factor between 0 and 1, right. Now, the wiring capacitance, as I discussed with you, the next is the wiring capacitance, is primarily the capacitance which appears due to a finite width and length of the connecting wires, and it is a function of the distance, which means that larger the length of the wire, more will be the cap loading or capacitive loading, and lesser the length, lesser will be the loading, right. So, higher is the cross section area, lower will be the loading, so on and so forth, but primarily higher the length, more will be the loading available to you, and therefore the capacitive loading will be much higher in this case as compared to the previous case. So, that is the wiring capacitance which you see in front of you. So, we come to the last part, which is CG3 and CG4, and it is nothing but the total gate capacitance of the loading gate M3 and M4. So, we have driving gates M1 and M2 are referred to as driving gates, since they are driving the circuit, and M3 and M4 at this stage is known as loading gates. So, the loading gates M3 and M4 I have got, and M1 and M2 are referred to as driving gates, right. So, I have got driving gates and I have got loading gates, right. So, C fan out is nothing but C gate of NMOS plus C gate of PMOS, because they are in parallel, right. Now, if you look very closely, this has been broken up into this part and this has been broken up into this part, right, and let us see how it works out. If you remember, Cox was oxide capacitance per unit area, the area under the gate is nothing but W into L, L is the length of the device. So, if you take a cross section of the device, this is your W, right, and L was nothing but between these 2 points the distance here. So, I will have a rectangular region, and therefore, W into L is nothing but the area under the gate, and therefore, this area is nothing but WL into Ln into Cox. Same thing happens WP into LP into Cox here. CGDO means overlap capacitance, gate to drain. Remember, we were assuming that there is no lateral diffusion, so they will be self aligned and therefore, there will be no overlap. But if there is a overlap, you will have a CGD0N and you will have CSGSON also available with you, right, gate to source. So, you will have gate to source overlap, gate to drain overlap for N type, and you will have gate to source overlap for P type, gate to drain for P type. Add all these together and you get the total inverter characteristics. So, we will give you numerical problems when we give you assignments to play with, and you can actually then use this capacitive modeling to find out the total capacitance available to you when you have a cascaded pair of inverters available, right. Please make it a point of understand that when you have a single device driving a simple capacitor and you have a cascade of inverters, the formulation goes a bit different, right, and we will be discussing that as we move along, but that the formulation will be different. So, the first question asked is how will you improve your speed? Very well, very easy, reduce your value of CL. So, what you do is you reduce your CL, right. We will discuss this point, do not worry about where it is coming from, but we reduce CL. So, somehow or other if you are able to reduce the total CL value by either making your overlap capacitance small or making your wiring length small, or you can making the oxide thickness of the loading gates to be large, Tox is large. So, if ln ox by Tox for loading gates will be relatively low, so on and so forth, I can reduce my CL and I can increase the frequency of operation. You can increase the transistor size. Why do you want to increase the transistor size? If you increase for example W by L, if you increase, your current ID actually starts to become large. When ID increases, for the same capacitance loading, I will require a lesser time to charge or discharge, and therefore the speed will be larger. But mind you, as you increase the value of W by L, you also increase the chances, or in reality you also increase what is known as the self loading. M3 you see, if you increase W by L, you will also increase for all W by L. So, if when M3 M4 W by L increases, then please understand Wn into Ln into Cox will also increase in a quadratic fashion, because you are increasing W as well as L, let us suppose, or even if you are fixing the value of L, even if you double the value of Wn, you actually double the value of the overall oxide capacitance. As a result, your delay will be further reduced. So, you have to be very careful and you have to optimize the whole problem in order to achieve the best flow. The third point is increase VDD, which is obviously to increase the value of ID, and your performance in terms of delay will be larger, but then you pay the cost of higher power dissipation, because VDD increasing means you are V into I into V is power. So, the power will go on increasing drastically, right. So, this is one of the areas which we look into. Now, let me come to the third or the fourth topic, subtopic of this whole discussion, and that is basically the optimal value of NMOS to PMOS ratio, right, optimal value of NMOS to PMOS ratio. What do I mean by that? So, you see, if you improve the widths or if you increase the widths of PMOS, W by L ratio of PMOS, my TPLH, right, TPLH low to high will obviously come down, because it's so if your W by L ratios are higher, right, your resistance will be smaller and your therefore delays TPLH will be smaller by my previous discussion. Also, as I discussed with you, in increasing the charging current. So, in both the cases your TPHL will be smaller, but it also degrades the TPHL, right, because of large parasitic capacitance. TPLH is what? High to low, right. I agree with you, high to low the PMOS will be cut off, right. Cut off means what? That there is no channel available to you, but you will still have gate to drain capacitance always available. You getting my point? My previous discussion. So, therefore, if you go on increasing the value of W by L, you end up also loading the pull down capacitance. So, pull down capacitance will become higher. So, it becomes higher even than the loading capacitance, right. So, let us suppose I optimize it by a factor known as beta and we assume beta to be equals to W by L of P divided by W by L of N, right. Now, we know that CL is equals to diffusion capacitance of P1 plus diffusion capacitance of N1 plus gate capacitance of P2 and gate capacitance of N1 plus the wiring capacitance, which we have seen just now. Now, what we do is obviously CdP1 will be beta times dN1. Why it will be dN1? Because you have increased the size of PMOS beta times as compared to NMOS, and therefore your capacitance will also become double that of NMOS, because it is totally depending on the profile parameter or on the device characteristics, and CGP1 will be also equals to beta times CGN1, right. As a result, if you just have to put this and this back into this formula, I get CL equals to 1 plus beta dN1 plus CGN2 plus CW, right. If you place this into 0.69 R equivalent into CL formula, I get this formula available to me, fine. If you take R equivalent outside, I can safely write down this to be 0.69 by 2 into R equivalent, right equivalent, and then this whole thing, right, plus 1 plus R by beta, where R is equals to R equivalent P divided by R equivalent N, right. So, R equivalent P divided by R equivalent N you get in this case, and this is 1 plus R by beta, right. This is what you get finally for the TP, and this is the most optimized design which is available to you, and for NMOS to PMOS ratios. The fundamental behavior therefore is that if now I have a TP relationship which you see in front of you, and I have R values available to me here, simply by deriving del TP del beta I can let you know the value of beta at which the TP will be minimum, basic mathematics. So, I take TP del beta equals to 0, after doing some manipulation, mathematical manipulation, I get this to be true, assuming that my wire capacitance Cw is very small as compared to CDN and CGN2, which is really the case, then I get beta optimum is actually equals to root of R. Now you see that is quite interesting, what I wanted to point out, that the optimal ratio here, what is R? R was basically equals to R equivalent, if you go back to the previous slide, R was equals to R equivalent P by R equivalent N, right. So, R equivalent P divided by R equivalent N, right. So, root of R, which means that if you make your R equivalent R larger and larger, your beta optimal will also increase. What is R? The ratio of the two, but ratio of the two will depend upon what factor? Aspect ratio. So, you have to make your W of P larger than W of N, agreed. But please understand one important issue, that when we were discussing a simple inverter and we were trying to fix our switching threshold in the middle of the whole VDD by 2 and assuming the threshold voltages are equal, we saw that we require only R, beta was equals to R only, remember, it was only R because R was equals to 1 and then we got VDD by 2, remember, and that was the case when both pull up capability and pull down capability was exactly equal, by making the widths of PMOS 2 to 3 times larger as compared to NMOS, and therefore the pull up capability was almost equals to the pull down capability available to you, and as a result it was perfectly symmetrical in nature, and therefore beta was equals to R. Now what we are doing is we are telling no, I do not want TPHL to be equals to TPLH, but I want that my total delay, overall delay should be minimized. For that I require this to be true, the root of R to be true. So, root of R basically means if it is 3 times, then the root of 3 will be available in this case, right, 1.7, 1.8 times, right. So, if you look at this graph in front of you, beta is basically, as I discussed with you, WP by WN. How? Because this is WP by LP, WN by LN, ln LP cancels out because they are equal. So, I get WP by ln equals to beta. If you look at this graph, this is propagation delay versus beta here, right. So, as the beta value goes on increasing, right, beta value goes on increasing, becoming what, your PMOS is getting more and more stronger. So, what is happening is your low to high is falling down, as I just told you, but and it falls down like this, right. But as the beta value increases, your high to low also starts to fall down. As you make a beta higher, TPLH starts to fall down because PMOS is getting stronger, but TPHL starts to rise up because your NMOS is getting weaker with respect to NMOS. So, your pull down device is weaker now. So, I reach at optimum point somewhere here. So, this black line is nothing but the summation average of these two. I reach at the point here which is somewhere here, right. So, between 2 and 2.5 is the value of beta at which you get the minimum value of TP available to you, right. So, this is the optimal inverter equation which you see in front of you. Now, let us look at how to size an inverter chain. A large number of inverters are connected in series to each other. So, how do I size my inverter so that I get a minimum delay, right. So, for a given value of CL, what is the minimum propagation delay between input and output, and what is the number of stages at which I will get the minimum delay available to me, and what is the optimum NMOS to PMOS ratios which is there. These three things we will be finding out over the next 5 to 10 minutes of work here. Now, any load capacitance which you see here will be composed of intrinsic capacitances and extrinsic or external capacitances. Intrinsic capacitances are what? Intrinsic capacitances are which is self loading capacitances, capacitance because of the drain and diffusion, and external capacitances are by virtue of wire, by external sources, by everything else you define, right. So, I define intrinsic as output capacitance of inverter associated with diffusion capacitances, and what is C external? Fan out and wire capacitances. So, CG3, CG4 plus CW is external capacitance, and CDB1, CGD1 and CGD2 are all diffusion capacitances, right, they are all intrinsic capacitances. So, the propagation delay with Tp will be equals to 0.69 into R equivalent into C internal by C external. I think this is clear. So, I get C internal, I take it outside, I get C external by C internal. The delay of each inverter will itself be delayed by a factor equals to 0.969 R equivalent by this thing. So, what I do is I replace this by Tp0. So, Tp0 is what, the delay of the inverter itself. So, what you see, what I am trying to say is that you have a chain of inverters, right. The chain of inverters, if you look, then this is CL, this is in, this CL is composed of C external and C internal and C external, or C intrinsic and C external. There will be a composition of C internal, intrinsic. So, intrinsic is what, because of gate and diffusion, because of drain and bulk, there will be internal capacitances. So, the inverter itself will get delayed by virtue of this, without being even affected by the next stage gate capacitances. So, as a result you get this as Tp0, right, and 1 plus C external by C internal. Sizing up an inverter, as I discussed with you, will reduce the delay, agreed, because you are actually making it much more faster because your current carrying capability is larger, but the cost you are paying for it is that it also increases the input capacitances. Now, input capacitance, the input gate capacitance, and suppose I say that internal input gate capacitance, and I have got Cg to be equals to gamma, right. This is basically a fraction, and the input gate capacitance and intrinsic output capacitances are function of gate, and we define that the intrinsic gate capacitance is gamma times the gate capacitance, because there will be some proportionality factor which is there. So, what I do, I just simply make it Tp equals to Tp0 1 plus F by gamma, because gamma is C internal by Cg and F is equal to C external by C internal, and therefore I get Tp equals to Tp0 1 plus F, right. F is defined as the effective fan out, right, it is defined as the effective fan out. Now, therefore, if you look at the delay, therefore, the delay of an inverter is a function between the ratio of the external load to its intrinsic capacitance, which means that the delay of an inverter depends on the ratio of the external load capacitance to its internal capacitance. That you can even find out at this stage also. You see, Tp is depending on the value of C external to C to internal or to intrinsic, and therefore I get a ratio between external load and the capacitance, right. Let us look at the sizing of it, therefore the sizing of an inverter chain. So, what I do, I get Tp equals to Tp1 plus Tp2 plus Tp3, there are n number of gates available. My driving gate has got input gate of Cg1, and my last gate, which is the final gate, has a load capacitance of Cl. So, going by the definition, I get Tp will be nothing but the sum of Tpj, j moving from 1 to n. So, there are n gates, each gate is giving Tp1, Tp2, Tp3, Tp4, you add all of them, you get the total Tp. Therefore, breaking down is Tp0 is the propagation delay for a single gate, which is that is constant, independent of everything, it depends only on the intrinsic gate, it does not depend upon extrinsic gate, therefore you can take it outside the summation sign, and therefore I get 1 plus Cg in gate input gate capacitance of j plus 1th one. Why j plus 1th one? So, if you are measuring for this one, if this is j, this will be j plus 1, right, gate capacitance of this one, divided by gamma times Cj on of what, of this one. So, this, right, and I say that Cg in n plus 1 equal to Cn. Why? Because this is the last, is this one, n plus 1 is the last stage which you see, the output gate the input gate capacitance. So, if there would have been inverter here, its input gate capacitance would have been equals to Cl, that is what I am trying to say here. So, there are n minus 1 equations, there will be therefore n minus 1 partial derivatives to solve for this quantity. So, I get delta Tp delta Cgi equals to 0, and then I need to minimize it, right. If you and solve for V, I get this as a relationship, right, and this is quite an interesting relationship which you see. You can see therefore that if you try to find out, I get Cgi, right, is nothing but square root of Cg j plus 1 comma Cg j minus 1, which means that the size of each stage is the geometric mean of its two neighbors. That is very, very important. That means if I have one inverter here, I have another inverter here, another inverter here, I need to be very careful that this sizing here should be at least is the geometric mean of these and this, these two inverters, right. You have to be very careful of that, and that is what is written as Cg in is equals to Cg in j minus 1 into Cg in j plus 1, right. That means each inverter is sized by a factor of f with respect to its preceding gate, right, as the same effective fan out, which means that if you therefore increase the sizing of individual inverter in the chain by a factor of f, where f I have already defined in the previous slide, then you will be able to minimize your delay under all conditions. So, we therefore define f to be is equal to CL by Cg1 square root of n, or nth product of that. This is the capital F, which is the effective fan out, and square root of m. So, I get f equals to small f equals to the power 1 by n, which we get from here. Therefore, the minimum delay is what? NTPO. Why NTPO? Because there are n number of stages. So, I multiply n with TPO delay of 1, that multiplied by 1 plus root of NF by gamma, right. Gamma was coming from the previous slide, right, where F represents the overall effective fan out of the circuit. Capital F represent the overall effective fan out. Now, if you see carefully here, carefully in this slide, then as you increase the value of n number of stages, your NTP0 increases, right, NTP0 increases, but at the same instant of time f to the power say 1 by 2, it becomes 1 by 3, 1 by 4, that starts to decrease, right. So, you will have two competing effects, and a time will come when they will cancel out each other and TP will have minimum value. The optimum therefore value of right number of stages can be found by differentiating the minimum delay expression to the number of stages and the result settling to 0. That is what I was telling you, that del TP del n set to 0 and then see which one is minimum, right. So, from that we get this expression, that gamma plus n of root f minus nth root of f by n equals to 0. The common practice is that generally the optimum fan out selected is generally equals to 4. So, this expression which you see in front of you will give you an idea about the number of expressions which you want, or number of stages you want for a delay chain to have a minimum value of gate voltage available to you. Before we move forward, therefore, let me recapitulate what we did till now. We saw what is the meaning of inverter delay, how does inverter delay depend upon the process parameters, which is W by L. If I have a single inverter driving a load and I have a cascaded inverter driving a load, how does the things change? What is the meaning of beta ratio? What is the primary meaning of optimized value of beta ratio, right? Then we came to the stage where we have inverter chain. In this inverter chain, we also found out that if I have inverter chain, what is the minimum number of this inverters I need to put in series so that I get the minimum delay. We found out that n to be equals to 4. We also found out that the effective fan out should be minimized in order to achieve a minimum delay. So, this was part which we have discussed there. Now, we come to the next section of our talk, and that is basically your power dissipation, right. In power dissipation, we have three types of power which is generally available, which is in a standard CMOS digital VLSI circuit. We have what is known as a dynamic power dissipation, right, dissipation, and we have a static power dissipation, and we have short circuit power dissipation. So, there are three types of power dissipation available to us: dynamic, static and short circuit. Dynamic, as the name suggests, is when the inverter is actually switching between 0 and 1 and so on and so forth, that we define as the dynamic power dissipation, and the inverter is switching between 1 and 0, right. Their active role of the load capacitor and the resistance offered by this NMOS and PMOS will come into picture. We look at the static one. When the device is either in the off state, then you will still have some leakage currents available to you, right. These are basically known as sub threshold leakage, or you can also have some leakage through the oxide layer because of high electric field. This is known as direct leakage, right, and you can have these. If you add those two together, they form about 5 to 10% of the total power dissipation available to you. We also have a short circuit dissipation. Please understand a very important issue. Remember, there was a time when you did have something like this, right. You also had a time when you had something like this, but there was also a case when both were saturated, was something like this, and this was VDD, which means during the switching threshold, exactly at switching threshold, both the devices NMOS and PMOS are in saturation, and therefore, for a very finite duration of time your VDD and ground are already in contact. So, there will be a short circuit available here, fine. So, there will be a short circuit which is available here, and there will be a short circuit current which is flowing through the device, which means that, which primarily means therefore is that, and why is it very short? Because I have discussed with you in the previous turn when we were discussing VTC, that if you look at this point, this is the point I am talking about, VM, right. This moves so fast, this movement is so fast across VM that it stays for a small duration of time, but in that small duration VDD is connected to ground, and as a result what will happen is there will be a sudden peak in the current from VDD to ground, and every time the switching takes place you will have always this short circuit current available to you. So, if there are 50 switchings, there will be 50 such short circuit currents which will be coming to you, and as a result that will also add to the total power in the circuitry, right. With this knowledge or with this idea I would like to stop here today, and give you what we have discussed today is basically the inverter characteristics. We have understood the static characteristics of inverter, how to draw the VTC, voltage transfer characteristics of an inverter, how to extract noise margins from inverter. We have also understood the basic building block of an inverter, what is the propagation delay of an inverter, what is TP-HR and TP-LH, how they are related to VDD and R equivalent and CL, how can I minimize the delay across an inverter chain, what should be the sizing ratio available to you so that these can be modified to a proper extent. With this I will just stop here, and we will start next time with the next definition of power dissipation. Thank you very much.